they are often really undervalued by us. We just treat them as one more object that comes from the context and we inject it somewhere. Thanks, guys. But yet they are the tool that makes our systems useful, because only thanks to them we are able to communicate with the outside world. So they come from some forbidden place. God knows where and when someone created them in our projects. Maybe they even came from the templates. My name is Dubiel, and for the next 40 minutes, I would like to talk about HTTP clients and why I think they are really the heroes of distributed systems. But before we get to the topic, short explanation. Why am I even here? And why do I think I have enough of experience to share it with you? So I work for Allegro. I've been working there for like 4 years now. This is the biggest Central European e-commerce business. We have something around 12 million users. Our IT division hires almost 600 engineers. And we started doing microservices before it was cool. So currently we have something like 350 microservices in production running on Mesos. And this means that we exchanged the pretty silent monolith, who doesn't talk much, to a very chatty system or architecture, microservices, which like to talk a lot. What's more, I'm also the team leader of Skylab team, and this is a very specific team because we are somewhere in the middle between business developers and the infrastructure. So we do this middle tier services for other services, and one of our major products is Hermes. It's our open sourced pub subsystem based on Kafka. But what's important for this talk specifically is that we work on Andamio, which is our JVM service starter. So it's basically a Spring Boot starter, but what we focus on are two things. First of all, we want developers to be able to start quick. That's pretty easy. The second harder part is that we want our developers not to make the same mistakes as their colleagues did. This means that we want to provide them with tools that are good enough, like reliable enough, fault tolerant enough. And this means that we are creating a lot of factories for the developers to use, because as you're going to see further on during my talk, the default values for HTTP clients are really insane. So we want to make them a bit more saner. Okay, let's define HTTP client for the start. So when you think about HTTP client, you probably think about this one of the objects of the classes that you actually inject into your beans. So it might be a REST template, pretty easy to construct that one. It might be Jersey client. It might be async REST template or Retrofit. And this is the things that we actually usually interact with. However, these are also like the things that we argue about. So whenever you start a new project, you might have had an occasion to argue which API is better. Like, do you want to REST template with this get for entity, or do you want this nice and smooth Jersey client fluent API to begin with? We also, argue about the asynchronous APIs. Like, is this verbose enough with all the callbacks? Or do we want Jersey with the .async thing? Yeah, so you can spend a lot of time arguing about which API is better for us, which client is better for us in this project because of readability, or is it easy to use, and all the superficial things actually. Because what if I told you that underneath they are all the same? Like, this is just the superficial API, but if we go deeper, we'll actually find out that they're all the same. So, let's do this. Let's go deeper. Let's start with REST template. So what happens when we call REST template.get for entity? Well, there's going to be quite a lot of methods to get there. So first of all, we go to the do execute, and then, by the way, Spring names are sometimes really crazy. So we go to HTTP accessor and create a request, okay? Then we go to client HTTP request factory to create the request. Then, and this is where things start getting interesting, we go to simple client HTTP request factory, and this is what happens when we do it on new REST template, like no on the defaults. We didn't change anything. And then there's a well-known class URL. We open a connection, which in turn gives us the HTTP URL connection. Okay, this is for REST template. Let's go with Jersey. Let's do the same exercise. So we do the get. It actually does some invoke. Then it does another invoke, apply, another apply, and now we're getting to the nice things, URL.open connection. So after all those stacks, we ended up in the same place whenever we chose Jersey or REST template. At the very bottom, what we do is call the same HTTP URL connection. And this is the thing that actually does all the hard work, not all the fancy APIs above. Okay, but async is really popular at the moment. So it surely has to have some superpowers in those async REST templates and all the other calls. Well, you're going to see that actually it doesn't. So in case of REST template, all you need to do is to add async everywhere to all the methods, and you're going to get to the same place. Just change the name of the async. Okay? Same with Jersey client, except that you can change all the invocations to submit. And further down the road, here we go. We're in the same place. Okay? So whether you're using async or simple clients, you still end up using the same thing, HTTP URL connector. So what I would like to say is just let's stop arguing about syntax sugar. I mean, well, maybe I'm being too harsh a bit. Like, you can say that APIs are very important because their readability, etc., etc. But for this, we can actually get back to this discussion about APIs, about the syntax sugar, once we resolve the important problems. And the important problem is, what the hell is HTTP URL connection and what it does? Because this is the thing that controls our application in one way or another. When your code runs in production, it doesn't care if you're calling Jersey or something. It cares who manages, the only thing that matters is who manages the resources. And in this case is this weird class. So this is the distinction I'm making here. So on one hand, we have the APIs. The APIs are the things that we interact with that make our life easier. And actually, all they do is add some layers of the abstraction. While on the other hand, we have the implementations. These are the guys that do the hard work. And these are the guys that we should be focusing on more than we do at the moment. So we have HTTP URL connection, Apache Client, an IO client, and OkHttp. We're going to see some of them in action in a moment. So this is the important part, and we want to focus on this one. So how to choose the right implementation for our project? Like, we already settled this, that we don't want to choose the right API because this is comes later. We want to choose the right implementation. So what you have to do is you got to start with the basics. And the basic thing is this. You might notice this. You might know this already. These are the 8 fallacies of distributed computing. I'm not going to go through them one by one because they are not so interesting for us at the moment. But these are like the basics. These are the 2 points that actually interest us in the context of HTTP clients. So, but okay, this is the base. So where do we go from here? What do we have to do to choose the right implementation? What you got to do is you got to ask yourself one question. Or, well, actually, you're going to ask 3 questions, but, the quote. So, first, latency is 0. Well, is latency 0? since it's a fallacy, of course, it's not. So let's start a mind process. Is latency 0? Of course not. So when do we pay? When do we wait for something to happen? Well, we wait when we connect to something and probably when we gather the data, when we receive the data. So let's start with paying for the connection part. Do I have to pay for creating new connections? Well, you don't if you use the right connection pools. So what is the connection pool? Connection pooling is a way to mitigate the cost of cost of creating new connections, and it's something used in very different areas, starting from database connections. But here we're gonna concentrate specifically on HTTP clients. So the thing is, even the presentation title, it says HTTP clients. So it's like we're here on the HTTP level, but when you look at the protocols involved in actually making the connections, we also have to think about TCP because, well, this is a crucial part of the whole HTTP stack. So we need to care about this as well. So whenever we make a new call via HTTP, the first thing, because, well, HTTP is stateless and connectionless and it's great, but down there, TCP is actually does connections which are persistent or can be persistent. So when we start a new call, what we do is we create a new connection. This is the yellow part. And then we go with our data, request and response. So if we have a lot of requests to the same place, does it have to be like this? Well, we pay for the connection part each time something happens. Does it have to be like this? And then we're going to bring in the second fallacy. Network is reliable. What if it's not? What if the connection part, which was so, small on this slide, what if it gets bigger, like here? What if actually setting up the connection takes a lot of time, and the request response is really fast? Do we want to pay this cost? Well, of course not. So the ideal thing would be if we paid this cost only once, and then, well, just did our work. So we always have to send request and receive the response, but we don't have to connect every single time. So this is the time when I'm going to show you some test samples and code on how connection pooling might work. So these are simple tests written in Groovy. It doesn't matter for this, but they are really verbose. So while it's not the greatest code ever written, actually it has probably some bugs, it makes the point. So what we have here is we are going to connect to the service on localhost, which has 1 second of delay, 1,000 milliseconds. And we're going to call it from 10 threads. First of all, we're going to use HTTP URL connection to achieve this. So let's see the test output. Okay, here it goes. So first of all, we're going to be connecting, waiting for the connections. Then after 1 second, all of them succeeded. Okay, and this was using the HTTP URL connection. This HTTP URL connection is actually a pretty peculiar piece of code. So it's default everywhere because it comes with the JVM. It hides somewhere in sun.misc classes. It's not really so easy to find. And when you look at the code, you can get pretty terrified because there's a lot of synchronized statements, and it's not really easy to figure out what it really does. So the thing is, it also has some kind of a keep alive or connection cache, which is not really configurable. So you can just set the global amount of connections to keep alive per destination. I'm going to talk about destinations in a while. If we bring in a bit more customizable tool, which is Apache HTTP Client, and do the same exercise, you're going to see what I meant by saying that defaults are insane. So it's the same code, just different client. We're using Apache Client. So once again, 10 threads, 10 connections going to the service, which actually has a latency of 1 second. Let's see what happened. Oh, instead of 10 results, we only received 2. Why is it that we only received 2? And there are some exceptions. So the thing is, by default, when you use Apache HTTP client, the default size of connection pool is 2 per destination. By destination, we mean host and port. Yes? So let's try to make it a bit better. This is the way to configure HTTP client to make it a bit better. So we set the default max per route. Route, once again, is host and port part. And there is a grand total of all the connections that can be kept in the pool. And when you run this code, after this slight tuning, we're going to see that this time it's actually working. So we got 10 connections, and they were able to succeed. Okay. So let's get back to a bit of more of theory. Goodbye, Kat. So what is a connection pool? So connection pool is a shared pool of resources. In this example, these are connections. And those connections can have different state. So whenever a connection is waiting, is in use, is waiting for for connection or for receiving or is sending data, it is in least state, the red ones. Whenever connection is available to use, it's in available state. That's easy. But as with all resources, the connection pools are not infinite, and we've just seen it in the example. So what happened when we tried to squeeze in 10 connections in a 2 connection pool? Well, as always, with all the resources, there has to be a queue. I mean, the queues are everywhere, and this is no different. So there is the third parameter of a connection pool, the Apache connection pool, which is pending. And this is the number of requests which are currently waiting for to get resolved. So managing the number of concurrent connections or connections in the pool is the first step to make your application actually run quicker or run faster. Why is it? Because if something is waiting in the queue, it's not doing its job. This means that if somebody throws too many requests on you, you actually are able only to do this much work in a given amount of time. And all the other clients are suffering because their connections are just waiting. So they are waiting for the other requests to stop. So the question could be, why not make it infinite? I mean, everything is so cheap, and let's make it infinite. Why do I have to bother? Well, the thing is, if something is infinity in computer science, it's just an illusion. So there is always the resource which is the resources are always finite. So whether it will be heap memory or number of available sockets, they're always something. And the only way to actually be aware of what you're doing is to control the number of resources you're using. Thus, we use pooling. But we want to be, able to do our job. So we want to make the pools big enough, but not bigger. And to do this, we have to measure them. So these are actually the 3 parameters of connection pool which you should always measure. It's the available count, least, so utilization, and the number of connections pending, so waiting in some kind of a queue. If you know a bit more about thread pools, it's totally the same, the same pooling mechanisms. Okay, so since we got with the latency 0, since we finished with latency 0 fallacy, let's go to the other one. So network is reliable. Well, is network reliable? Or are my peers reliable? Because it's also talking with your peers. Well, of course they are not. I mean, you've probably seen a lot of network outages. So how can I know if somebody fails? Well, the only thing you can do is actually to set some kind of a timeouts. So let's dig deeper here. Like timeouts, what are the timeouts? There are actually two kinds of timeouts which are really interesting for us in context of HTTP clients. So the first one is connection timeout. As I've shown earlier, connection might take, connections are usually really quick, but sometimes, and this is the moment when you want to be able to react quickly, sometimes they're really slow. But these slow connections don't happen when you're at work and when you have a laptop open and you're in a reliable Wi-Fi radius. These things, those incidents happen at 3 a.m. on Sunday after you've been going to the parties all night. And then you have to react. So why not make your life easier beforehand? So, it's like you're trying to connect and then, this used to be faster. Like, I remember it being faster. Like, should I grab something to eat or something? Okay, it's like, you're waiting for the bus and you're like, okay, if it doesn't come in 1 minute, I'm gonna go. And then it actually arrives. Okay, works again. Well, it's not really working. It took too long to connect. So what we can do is actually, configure the connection timeout so it actually stops earlier. So it frees the resources earlier. Because what happens while the bar is green is we're not doing our job. We're not doing anything, actually. We're just waiting. And if we're waiting too long, our customers will be angry. Our resources, our connection pools, our memory might be, depleted. So we have to fail fast. And so connection timeout is a time between initializing the connection and actually making it happen. And we can amortize this cost by using connection pools, but even if we have connection pools, we have to make the first connect anyway. And the thing is that defaults are insane. Once again, they depend on the systems we're running on, and they are measured in tens of seconds. We're going to see this in an example in a minute. And so sane defaults, we need to give some sane defaults. Of course, you should measure the thing, but for me, sane default for connection timeout is something around 200 milliseconds. So compare this to the tens of seconds as the system defaults. So socket and read timeout. This is the other kind of timeout which we should configure. So while in the connection timeout we're waiting for just making the TCP session open, here we are actually already made the contact with the other party, with the other service. We probably even sent our request, so the guys out there know that we want something from them, but they are really slow. So they might have even started sending us some data, like we got the first chunk of data and we're really excited. But then something happens and we wait. Oops. No, not this. What happened? Okay. And we wait. Yeah, yes. And we wait and we wait. We're waiting for more and more data and nothing comes. And once again, for us, this means that we're wasting our time. So we might be lucky and the other service might be alive and it will respond in 10 seconds. But we might be unlucky and the service is dead and we'll be waiting and allocating our resources for hours, like maybe not hours, but a lot of seconds, minutes. So once again, the only remedy for this problem is to set timeout and fail fast. All the microservice talks say you have to fail fast, you have to have a quick feedback loop about whether your peers are working or not. Well, timeouts are the way to achieve this. So socket timeout or read timeout, as it is sometimes called, different APIs use different names, is a time between receiving the consecutive pieces of data. So even if I received first chunk, but the time between first and second chunk is too long, we can still timeout because the only thing that matters is after I received the whole data, not just part of it. And once again, defaults depend on systems, but in this case, the defaults we would like to set for ourselves depend on our peers. How do they react and what's their response time? Because if we set socket timeout too low, so we're communicating with other service which 99th percentile of response time is 1 second, and we set response socket timeout to 100 milliseconds, we're going to time out every time, or most of the times. It doesn't make sense. So we actually have to have some knowledge before we set this timeout. And different kind of SLAs are a great tool to achieve this. So if somebody else can guarantee any kind of an SLA, like we're going to respond in 100 milliseconds, then you know what should you set as socket timeout. It can be 200 milliseconds or something like this. So this is the tricky part where you have to actually measure things. And let's see them in action. So once again, getting back to my keyboard. I have some more tests. This time, let's see the default timeouts. So the only thing that changed here is that I'm not actually using any thread pool or spawning multiple threads. I'm doing this in a blocking old school way. So I'm just calling request. And this time, I configured the other service to respond with 10 seconds of delay. So let's see if it's going to be enough for us. So I'm using system timeouts here. And this is what happens. I'm waiting and waiting. I'm getting hungry. And this is what your customer is thinking. Like, you know, I clicked the button and I'm waiting and the payment is not through yet. And did something happen? Or oh, yeah, it timed out. Is my money secure? Well, you have to wait. We don't want to wait so much, so long actually. So the thing to do is to actually configure the timeouts. And this can be done quite easily. We don't need this one. So I'm going to set the socket timeout here. 50 milliseconds is probably too little, but 1 second, yes? So we're going to see it in action this time. And I added a bit of code here just to measure how much it took to actually time out. So let's see the results of this test. Yay, we actually timed out. So the service wasn't bound to answer us before 10 seconds elapsed. And yet we actually, you know, gave the feedback that, well, I cannot because I'm not receiving any data. I have the connection, but the read timed out. And it took like, 1 second, exactly as we wanted. So we have the, quick response, and now we can tell our client that something is not right, maybe, or do something else. Okay, this will be too easy. So as always, there are some caveats. And let's try the same thing with async client, synchronous client. So this is the same code, except it uses a synchronous client, and we just block somewhere on the future to make it, appear synchronous. But we're going to see something really funny here. So I've set the socket timeout to 1,000 milliseconds. Let's run the test. And, oh, it worked. Okay, 1,000 milliseconds is okay. Well, let's say I'm really impatient. My clients are really impatient. I have a lot of traffic, and I cannot, afford to actually stall for 1 second because I'm eating up all the resources. I want to stop after 100 milliseconds, so I'm not going to wait longer. Let's do it once again. And we're waiting. You see why I added this measurement? We were waiting for 1 millisecond. We defined that we wanted to wait for 100 milliseconds, and still we waited for 1 second. So there's something wrong here. Well, it appears that actually you can set the timeout, but when you think of it, what actually does the job of timing out the connection? There has to be something that goes around, that checks the connections and times them out or not. And indeed, there is a thread dedicated to this job, and it's actually running only every n milliseconds. By default, it's 1 second. So even if you set, even if you set 100 milliseconds of timeout, if you don't change the other setting, like here, it's going to do nothing. And this is a really important lesson because, you might think that the APIs you're using work in some way, but you're actually not going to know it until you try it. So if you're not going to make this timeout to appear, you're never going to know if it worked. See, it timed out after 200 milliseconds, short of what I actually wanted. Okay, getting back to slides. Go. Great. So there is another thing that it's outside of the fallacies, but there is one important thing when thinking about clients, and it's called the thread model. So in our minds, we're really used to thinking about synchronous things, about synchronicity. So, and this is the perfect model in which REST templates operate. So by default, IO thread model looks like this. We have some thread, which actually is blocked for as long as we're not receiving any response. This is what I said about blocking our resources. So we're just waiting, and then it comes, and we have it. Yes, it's really easy to grasp. It's the way we operate, the way we think about time. But it might not be efficient enough in a lot of cases. That's why there's the other thing called the, so this is all the times that we're waiting for. So we also have this other model, which is an IO thread model. And it gets a bit more complicated, but it's really important to understand it to be able to get some benefits from it. So you see there are more actors here than they were in the previous slide. So let's say we're making an HTTP call somewhere. From my thread, the green one, it's running. We have to block it for some time just to make the call, just to make the execution. But what happens next is it actually gets freed because all the work is done by a specialized group of threads, which are provided to us by the HTTP client. In this case, it would be async NIO Apache client. And those IO threads are very special threads. There's very little of them, but yet they work tremendously well, and they do not block. Why is it? Well, all they do is actually care about the I/O. So their mission is to put your data on the wire and read it from there. Nothing more. They're not waiting. So the I/O threads, it's a pool. It's usually something around 4 or 8 threads. They make the call to the OS. Yes, all the connections are in place. And then what happens when they will be, doing some other work in the meantime. They're not waiting. They're not blocking. Because as soon as the data arrives on the socket, the OS is actually waking them up, is giving them a notification that, hey guys, there's some data on the socket, why don't you pick it up? And this is the place where they start getting busy once again. So as you see, instead of blocking for eternity in one place, we're able to do a lot of job thanks to the operating system mechanisms and move forward faster. But the important thing is, and this is once again a trap actually, is that be careful not to do much in this thread. Well, why would you do anything in this thread from the first place? Well, it appears that when you use this async NIO Apache client, your callbacks are actually called in those IO threads. This is the way Spring works around them, and Jersey as well. So, you might want to do some database call or call another service. Don't. Just read the data. If you want, fork another thread, make all the heavy lifting in the other thread. Because otherwise, you're going to be blocking in an IO thread, which is actually a very scarce resource, and you want it to be spinning all the time, reading from sockets and writing data to sockets, not doing some lousy database calls. Leave the database calls for your user space threads, the threads that you control and create. So once again, there are different implementations for IO and NIO. So we have the HTTP URL connection, of course, Apache HTTP client, and surprisingly, OkHttp, which is as well just a simple I/O client. You might have heard otherwise, and they have really good documentation and sites, and they're really appealing to use. But they are still just using simple I/O. It might be enough for you, but just remember about this. On the other hand, we have NIO clients, and this would be the Apache async HTTP client. There's a bunch of netty-based clients. There are some undertow-based clients. These are the guys that do the work, really asynchronously and in a non-blocking manner. So there are the questions which you always need to ask when you want to choose an implementation. The 3 questions I mentioned at the beginning. So, is there any connection pool, and how big is it? What are the timeouts? How can I set them? And what is the thread model, and does it suit my purpose? Like, if you want to have a lot of concurrent connections, a lot, like hundreds, you probably don't want to spawn new thread for each and every of them. You just want to go with NIO. It's going to be a way cheaper way to achieve the goal. But then, now that we've covered the implementations, we can get back, to the APIs level, the things that are familiar to us. Because, we already know what matters. Now let's get back to them. You might be wondering, because, like async RestTemplate or Jersey async calls, their APIs look, like they're not blocking anything. So, so for this thread model, once again, you have to ask yourself just one question, which is, if my code doesn't block, who is waiting for everything to happen? Like, there is no magic. I told you, there are blocking things there. So who's blocking? So what are the async APIs actually hiding from us? When we do a call from my thread and we call async RestTemplate, okay, we've called it. And then we have the remote service. And the weird thing in between is the magic. Like, we don't like to, look under the hood too much. It just happens. Somehow, it just happens. Well, there is no magic. It's just somebody else's threads. So while async REST templates want us to believe that they are non-blocking and reactive, whatever, if you don't check it, if you don't use the proper implementation, you're just going to operate on a different thread pool. So it's still going to spawn a lot of threads, and those are the threads that are going to be waiting, and you can see them in stack traces. They're just hidden from you. And it's a nice selling point to show that your API can be created using one constructor. There is, of course, a constructor in which you can, give your own thread pool and manage it. But, the default is that it's just going to spawn actually unlimited amount of threads just to be able to handle your connections. So as much connections are going to throw at it, it's going to spawn as many threads in a simple executor example. So if you're at the point when you've already chosen the implementation and now you want to choose the API, ask on which thread is actually which thread are the things happening? Whether it's my callbacks, what are the threads that operate my callbacks, or what are the threads that wait for the connections? And how big is this thread pool, and how can I actually configure it? Or maybe I don't have to maybe I can use the NIO one. But these are like the questions which you should always ask, because there is no magic, once again. And so, just to sum up, whenever you're in front of a decision, please remember, concentrate on the important things, not the syntax sugar, because syntax sugar doesn't really matter when it's the incident time. When something goes wrong, nice reactive or fluent API won't save you. The only thing that can save you is proper configuration of your implementations of HTTP clients, using the proper implementation and configuring it in a proper way. So that would be all from me. Thanks you all for listening. If you would like to reach me or work with me, I'm working in Allegro. These are our pages, and these are my contacts, personal contacts. And I'm happy to answer any questions you might have. There's a question. It's a long way for the microphone.
Thank you. My question is, which implementation did you choose in Allegro and why?
We're using, okay, in some parts of our system, some guys are using OkHttp because it has, it's actually the only one that really, okay, is the one that's easy to use and supports HTTP too. But the default is actually the async HTTP, async Apache client. This is the default for us. Well, because of the properties that I've been talking about. There's another one.
So my question is, when you are dealing with a microservice architecture, how much of the HTTP client's configuration and usage you would like to standardize between all of the teams, and how much freedom you would like to give to the application owners?
So our goal is to provide the teams with tools which they can use, but they don't have to. So if you want to make your application, good enough in terms of reliability when you start up the new project, just use our factories, and you can be sure that the pool sizes are configured like for the standard cases. The timeouts are pretty good. Of course, you should tune them for your own. But on the other hand, if you've seen the newest technology somewhere and you just want to grab it and use it, and we didn't cover it for you, like my team didn't cover it, so just go ahead, but remember to ask yourself those questions and configure them properly. Because if something happens, like there's going to be an incident, it's going to be on you. It's your responsibility. But you have the freedom to choose whatever you want, as long as you make it work in a proper manner.
Oh, no, sorry. I have one question only related. Are you able to propose some kind of source of information about this? Because, for example, I would be interested to optimize my HTTP clients on my project, and from where I could get the information like this, because here they are on presentation, but maybe.
Okay, I'm going to share the slides.
Okay.
But anyways, I don't think I can think of one place where you can, read all of this. Actually, if you just if you decide on an implementation like you got Apache HTTP one, just go through the configuration option in Java docs, and you're going to probably see a lot of unobvious and foreign terms. But for the ones that you know what they do, you can actually configure them. So just don't touch anything you don't know what if you don't know what it does. So that's the rule of thumb. One more here.
Thank you. I'm just wondering what should happen to the server to make the connection time longer than the actual processing time. Because the only situation I can imagine is that too many clients keeps the connections and another clients cannot connect, and in this situation the server administrator just turn off the keep alive connections options.
Well, actually,
what should happen?
Yeah. So actually, I didn't say this, but when you're running your applications or any kind of cloud thing, like, I don't know, OpenStack maybe, sorry. So, you're not actually, there is a lot of parties involved in actually making a connection. So it might be that there are some contrail issues, like the software that actually checks if you can connect from one place to another. So there are a lot of issues here, not only related to the server itself, because the server might be really fine, but to the network in between. So it's usually kind of a network issue with this. Okay, thank you guys. If you want to talk more, I'm available.